All right, so let's talk about the Simpson's rule. This is a way to integrate functions and solve ODEs with a very high degree of accuracy. So there's a lot of different things that we need to talk about before we can come to the conclusion of the Simpson's rule. The first one of those things being we need to define what an interpolating polynomial is. So in order to do that, we need to try and come up with a polynomial, and let's examine let's just imagine 3 points right now. All right, so we want some sort of polynomial that's going to pass through these points, right? Let's make it, the picture be accurate, right? Like that. Okay, right? So that means that if this is our polynomial, we normally call it P2 of x, meaning it's a second degree because we have 3 points, and that will become more apparent when we start putting down the math later on. We can see that at this point we have to equal if these points belong to f of x naught, right? If this is x naught, x1 and x2, right, where this is f of x1 and this point is f of x2. We know that, right, P2 of x naught must equal f of x naught. And so likewise for any point xn, we must equal the function value at that point. So how can we construct a polynomial that does this? Well, the idea is we're going to create a polynomial, first of all, that is 0 at all the other nodes and then 1 at the other nodes. So this is going to be the x1 polynomial, and then I'm going to draw you the x2 polynomial. Just want to make it very crystal clear of what these basis polynomials are doing, except for this one. All right, for this one we actually are going to be up here, and then for this one, let's go back a little bit. Let's make this right like that in the middle and over here. Sorry about that. So this is going to be our x0, our x1, and our x3 polynomial. And so, like I said, at all the other points we have to equal 0. So it might look something like this, or like that, or like that. And that's not exact. Let me redo that last one. It's going to look something like that. Doesn't matter, not important. But what we need to notice is that it needs to be 0 everywhere that the function value is not popping up. So what if we, all right, so say we have the formula for all of these and we want to superimpose them on top of one another. Let me kind of take this picture and shrink it down. Let's just kind of think about this. We'll put this over here as just a thought. So what I'm going to do is I'm going to create what I'm going to call the L this is for Lagrange interpolating polynomial. I'm going to create the Li node. And this is going to be x minus a point that it is not at, x plus the xi plus 1 node, times x minus another node that it does not exist at, right? Because we want to avoid the function being 0 at the point that it exists at, so we wouldn't want to create a 0 in the numerator here. This is going to be a fraction, right? And then, right, we said we wanted the polynomial to be equal to 1 at the point xi. So I'm going to do that. So when I'm at xi, on the top I'll have xi minus xi plus 1, and on the bottom I want the exact same thing, xi minus 1. There we go. And so we've created one of our interpolating polynomials. All right, so that's cool. Now we know that at some sort of value, right, this could correspond to either one of these, depending on what we define I to be. right? But we know that at the point xi, right, we can check, right, at xi, li will equal xi minus xi plus 1 minus xi minus 1 over, right, this doesn't change, right? This is a constant, this is a number. And so this is equal to 1. And so that's really handy because that's just a number. That's 1. We can multiply that by anything and get back whatever we got. So I want to multiply, right, we need to go and think back to this thing we said earlier. At the function value xn, I want my polynomial to equal this. So I'm simply going to multiply by that. So I'm going to start constructing P2 here. Right, so I'm going to have 3 points, I've decided. At the central point, I'm going to have f of x at I times L I of x, right, because this was a function. So that's just going to be one part. And so as you might imagine, we need other pieces of this puzzle. We're going to have f xi minus 1. Oh. Right, and then li minus 1 times x, and then the other point, x I plus 1, I plus 1 of x. Right, so let's quick talk about exactly what the other basis polynomials are. So let's get them all out over here. So we're going to have this one. All right, and then hopefully you'll start to see the pattern, and we can do this up to as many, as high a degree polynomial as we want. We're just going to have more and more points, and I'll show you guys the general form of that in a second here. So for the li minus 1 node, we're going to have x minus something that's not xi minus 1, so xi times x minus xi, where are we, minus 1, so plus 1, right? And then I'll divide by my node, xi minus 1 minus all of this stuff on top, right? So xi minus xi plus 1. Okay, right, so this is going to again ensure that we are 0 at all other function values other than xi minus 1, and then at xi minus 1 will be equal to 1. Therefore, we can multiply by f of xi minus 1 and get back the function value. So then our last one is the I plus 1 node. Right, exact same process. We do this sort of subtraction on the top where we find nodes that we are not located at. Right, we're not at minus 1. And then we force the function to be equal to 1 everywhere else, just at the point, right? So xi plus 1 minus xi plus 1 minus I minus 1. Okay, and so there's actually a much simpler way to write these. So what I'm going to do is I'm going to say, in general, Li is equal to the product of x minus xn, I minus xn. And then this set that we're going to index this product over, let me give it some room. This is going to be n in I minus 1, and then I plus 1. And then we're going to take away from that set is the case where we have I, but I is equal to n. So what we're saying is we don't want to have the case where we divide by 0. That's all that this little extra part takes care of. And so basically, I'm only writing this in a more complicated way because at the end I'm going to write a big generalized form. So we'll keep this in mind. Okay, so let's construct P2. Let's write out exactly what it is. Well, there's really no need to do that, I guess. Oops, I just had it twice there, I guess. So, all right, let's bring that down. Let's go to a new page here. So we have this. Okay, so now the idea is, okay, what do we do? What do we do with this? Right, we have this polynomial that interpolates successfully it goes between our 3 points, xi minus 1, xi, and xi plus 1. And so what we're going to do is we're going to integrate that, right? So this is what the Simpsons rule does. The Simpsons rule is an integrator. So then I'm going to say that I called it sk. So Simpsons rule for the kth node, this is going to equal the integral from, and bear with me, k minus 1 to k of p2 x dx. But this is going to be the kth p2 of x, right? Because we're going to have multiple nodes where we're integrating this. And this will become, again, more apparent when we write out the full definition. So ignore the k for now. It'll make sense in a second. So we have to integrate this polynomial. And so the way we do that is it's a polynomial, so we can integrate term by term, and there's no surprises. So let's start with the first part. So we can rewrite this k minus 1 to k f x I. And then do we need k or do we need I? I think we'll actually need k. X, k, l, k, x, dx. I might get the indexing screwed up a little bit here. Plus another one. X, this is going to be, right, k minus 1, L, k minus 1, x dx. So we'll do each one of these integrals separately because it's going to make it easier, because we're going to have some substitutions that are going to need to take place. F of x, k plus 1 times L, k plus 1, x dx. Okay, so I'm going to name these 1, 2, 3, and let's start with 1. So, right, the reason I wrote these all down, we can, right, copy this. Okay, so let's integrate this. We're going to multiply this by f x, and I'm just going to call it I for now. We're going to ignore the k notation for just a little bit. All right, I'm going to integrate this from I minus 1 to I plus 1. Okay. So this is, might look like a bit of a task to undertake, but what we're going to do is we're going to simplify a lot of things. So the first thing we're going to do is take that f and pop it outside of the integral. Let's make some space on the screen here. And we're really running out of space. Let's actually shrink it down here. How about that? There we go. Okay. And then we said we wanted to move you over here. Okay, there we go. All right, so, and now we have a lot of different variables in the integral right now, but we're going to take a look for a second here. What if we have, right, so when we have xi minus xi plus 1, we can actually rewrite this, right, because assuming, let's go back over here for a second, assuming that these are all evenly spaced, right, these are all evenly spaced, that means they're separated by dx. And if you know the Simpsons rule, you were probably looking for that. You were probably saying, where is his dx? He forgot to talk about it in the beginning, and you'd be right. So I have xi, right, which is not shifted by anything, but then I actually have xi plus dx, right? And so that means we have xi minus xi plus dx, which is just equal to dx. Right, and so we're going to repeat this process a lot when we're doing these integrals. We're going to have, let's see, we're going to have 6 different places where we're going to need to do this sort of analysis. So let's take a look. Let's rewrite with just dx's. So we're going to have f x at I, integral I minus 1 to I plus 1 of, let's see, we've got the same thing up top, or let's simplify the top, right? X minus xi minus dx times x minus xi, and then plus dx, right? If you're keeping track of the signs there. And I know most people aren't even watching this part of the video anyway, and they're probably just skipping ahead, right? But then we said this was dx. And then if we look at the other part, right, so this is one of the pieces of the denominator. We have xi minus xi, and then minus dx. So this is actually equal to plus dx. So actually on the bottom here, right, we don't just have dx, we have dx. I should really use something other than dx. Wow. Okay, let's go back and call this delta x, right? We are not talking about the infinitesimal change of x. Geez. Okay, so again, one more. Change delta x, right? Important distinction there. We have delta x squared dx. Okay, the next thing we're going to do is we're going to simplify a little bit more. We have f xi I minus 1 to I plus 1. And now on the top here we have x minus xi. What do we have? We have x. Should we simplify? No, we're not going to. We're actually going to pop the, oops, forgot the dot on the I. We're going to go back, pop the, we're going to do 1 over delta x squared times x minus xi minus delta x, and then we're going to do times x minus xi plus delta x. Okay. All right, so what do we do now? All right, this is too hard. This integral, I'll be frank with you, this integral is way too hard. It takes a long time. We have a lot of different pieces. We start cubing things, and then we have to plug in xi and xi minus 1, and it just gets really, really messy, and we start having to do cubic expansions, and it's not good. So what we're actually going to do is, I see the same variable, this x minus xi thing, I see that in both. So what I'm actually going to do is I'm going to substitute. So I'm going to say that u is equal to x minus xi, and then completing the u sub, we have dx equals du. Okay? And then we have to change our bounds. That's going to make this process a lot easier. So u of x I minus 1 is equal to x I minus 1 minus xi, which is equal to, right, we talked like this before, xi minus delta x minus xi, which is going to be equal to minus delta x. And then we have u xi plus 1 equal to xi plus 1 minus xi, which should be equal to xi plus delta x minus xi, which is equal to positive delta x. Okay, there we go. Now we have, and I'm going to save this because we're going to actually use these for all of the integrals. Right, once we do this once, this is going to be a lot easier to do again. So I'm going to put this over here. Okay, so let's rewrite. So we have f xi times 1 over delta x squared, times a new integral, which is the same integral as before, negative delta x to positive delta x of u minus delta x times u plus delta x dx. Okay, and then this is a lot easier because now we have a function multiplied by its conjugate, and so we get a quadratic that we can easily take the antiderivative of. Negative delta x to positive delta x, we're going to have u squared minus, right, delta x squared dx. right? So now let's do the antiderivative. We're going to have f we're going to have 1/3 u cubed. Oh, this is not dx, this is du. Haha. Why didn't anyone tell me? Okay, u cubed minus u times delta x squared. And then we are going to evaluate from minus delta x to positive delta x. And this is the part where I get nervous, because if I screw this up, then I gotta go all the way back and start the video over. Okay, so we have xi over delta x squared times 1/3 delta x cubed minus plus delta x cubed. And is that correct? Let's think about it for a second. So, right, because we have that's going to turn into positive. Oh, nope, I did that wrong. No, we gotta just do one at a time, right? So this is, I was getting ahead of myself. So we have 1/3 u cubed minus delta x cubed, and then minus, but it's plus 1/3 delta x cubed, and then we have plus, so this is actually minus delta x cubed. So what do we have here? We have 2/3. We have f of xi over delta x squared times 2/3 delta x cubed, which is going to be equal to f of xi times 2/3 delta x. Okay, so this is important. We're going to keep this in mind. So that was number one. All right, we're 22 minutes into the video, and we've done number one. So now let's do number two. Okay, let's copy number two, write L2. Which one did I say that was? That was the k minus 1 term, so I'm going to copy that. Copy. I'm going to put it here. And now that I explained everything before, we're going to kind of skip some of the crucial steps. So, I don't need red. All right, F. Okay, so let's get this guy. So we're going to start by, I'm going to rewrite everything in terms of the delta x, and I'm also going to move the f outside of the equation. So I have f of xi minus 1 times the integral, let me write that better, I minus 1, I plus 1. We have x minus xi, right, there's no delta x there. And then we have x minus, and this is going to be x minus xi, and then minus delta x. We have the dx over there, and then we're going to divide by, we have xi minus 1 minus delta x. This is going to be minus delta x. And then let's see, we're going to have minus, over here we're going to have xi minus delta x minus, what do we have here? What is this guy? We have 2 delta x squared. Okay, now let's perform our u substitution. So we're going to have f of xi minus 1 times I minus 1, I plus 1, and then we're going to have, right, u, oh wait, but right, from the top, right, I'll copy this. Right, we'll keep this in mind, like I said before. So we have what do we have? We go from negative delta x to positive delta x, and then we have, let's see, we have u times u minus delta x over 2 delta x squared du. Okay, so let's finish the problem. We have f xi minus 1 times, and then we have, let's do the antiderivative here. Actually, no, let's go one more round of simplification. U squared minus u times delta x du, and now we have fxi minus 1 over 2 delta x squared. That's not a minus sign. And then we have the 1/3 u cubed minus 1/2 u squared times delta x, evaluated from negative delta x to positive delta x. And so we'll plug in. One second, I'm going to cut this part out of the video because my computer's going nuts. Don't know why. Okay, resuming now. So we have this 2 delta x squared, and then we'll have 1/3 delta x cubed minus 1/2 delta x cubed, and then minus, but it's plus 1/3 delta x cubed, and then let's see, we have a minus again, 1/2 delta x cubed. Okay, so what do we have here? I'm going to double check my math, make sure this is right. We have a minus there. I'm just going to make it, oh no, this is a plus. Okay, so inside of here these cancel, and we're left with fxi minus 1 over 2 delta x squared 2/3 delta x cubed, which is equal to, right, 1/3 fxi minus 1 times delta x. Right, and that's good. Okay, so that is number 2. And let's do number 3. We're almost there, ladies and gentlemen. Okay, so number 3, third polynomial that had was the +1 case. Okay, again, we can delete this, add f of xi plus 1 in there, and integrate from xi at, I put it like this before, I minus 1 to I plus 1. Okay, so let's figure out what our function looks like. First of all, let's move f I plus 1 to be on the outside. And then let's see, we have x minus xi, right? We know that guy. And then x minus, no, not xi, x minus xi plus delta x. And then we're going to divide by xi plus 1 minus xi. But let's write, we forgot to, right, this is xi. Let's think, so we have over here, we have xi plus delta x minus xi, and then right here we have xi plus delta x minus xi plus delta x. So here we have 2 delta x squared, and here we have delta x. I think that's correct. Yeah, that looks right. So we have another 2 delta x squared. I think one of these terms is supposed to be minus. I think we need to take a second look over here again. So this is xi minus delta x minus xi, and this was xi minus delta x xi minus delta x, so that's positive 2. It's positive delta x. Okay, we're just gonna roll with it. Okay, so we have this. We're gonna do this again, and let's bring back down our u sub. Okay, here we are. So now let's substitute once again. We're gonna have f xi plus 1 to delta x squared times the integral from negative delta x. See how this is getting faster, right? Of u times u plus delta x. Yeah, u plus delta x over nothing. Yeah, over nothing. Right. Du. Okay, and so then let's anti-derive. I'll write this down here. Fxi plus 1 over 2 delta x squared times negative delta x to positive delta x u squared plus u delta x du, and this is equal to f xi plus 1 over 2 delta x squared. No, we're done integrating, right? Or we've integrated. 1/3 u cubed, 1/2 u squared delta x from negative delta x to positive delta x. Okay, so our last integral, right? We have f xi plus 1 over 2 delta x squared times 1/3 delta x cubed plus 1/2 delta x cubed plus 1/3 delta x cubed and then minus, but it's actually plus 1/2 delta x cubed. So now that we have this one, I'm actually a bit nervous that we've got it wrong. I found it. Okay, this was actually supposed to be a minus. That's it. And so we have the same number as before, which we should expect, and I'll explain why. So this is not 5/3, this is not 10/6, this is not 5/6. This is actually going to be 2/3 again, and so we get 2/3, yeah, 2/3, which we wrote at the same time, which is 1/3, which is, I believe, no, it should be, is it 1/3? Yeah, it should be 1/3. It should be the same as the last one. So there we go. And so the reason that these should be the same, that 2 and 3 should be the same, if we go back up here, these were if we go all the way back up to the top, there's nothing intrinsic about this point versus this point. So the quadrature, the amount that we add to each one in the Simpson's rule shouldn't be different, because we didn't have any sort of preference toward a left or right hand side. So let's write out exactly what our Simpson's rule is now. So we have, for the quadrature, we have that the integral, I called it sk, this is going to be equal to, let's go back up to the top here. We said it was the integral of all of those three. So we have delta x, let's get delta x over 3 times, we are going to finish this. Now we have, right, so the first one that we had, we'll put 2, 3, and 1, so we'll put them in order. So 2, the result from 2 was 1/3, so we have 1/3 of f of xi minus 1. And then let's look back up. What was the f of xi node? Okay, there were 2 of them. And then we, from right here, have just 1/3. Okay, what is going on with my pencil right now? Okay, so this is going to be just the formula for just a 3-point Simpson's quadrature rule. And so what I'm going to talk about next is how we actually expand this into being the full Simpson's rule for any number of nodes. So let's do that. So let's go back up to the top here. So before I just had 3. I just had this one, this one, and this one. So what I'm actually going to do now is we're going to consider groupings of 3. So I'm going to go like this, and then the next one I'm going to have is going to be over there. And so what you'll notice is, okay, how do I index this, right? How do I tell my formula where I want to implement these rules? So I'm going to go back up, and I'm going to say, okay, I don't want to start over here because this point doesn't exist. Right? I want to start at the 1 because my 0 point and my 2 point are going to exist. But if I start at here, now I don't want to do that because now that means I'm going to double count both of these sides. So what I'm going to do is I'm going to do my 3-point rule, but I'm going to do it at only the odd numbered nodes of my mesh. So let's go back down here and let's kind of draw that out. So this was just for 3 points. So let me get that going. So we just had 1, 2, 3. And now that means we're going to have, this is all going to be all times delta x over 3, right? So we have 1 of these, 2 of these, 1 of these. Okay, so now let's extend, right? We're going to extend out to the right, and we're going to see what happens when we add more points. So I'm going to say, here was my first grouping, and now here's going to be my second grouping, right? Now this is good, so this was my first grouping, this guy, and then the second grouping is on the right. So we have 1 from here, right? But then we're going to get another 1 from here, and a 2 from here, and we're going to get another 1 right there. Okay, so I found some errors. Back in the very first integral, the first error I made was right here. This is actually going to end up being a minus delta x. So we can put a minus sign in front of these calculations, a minus sign here, and that actually makes this become a plus sign, which is another mistake I made, and that also, I think that is it. But what ends up happening is we get 4/3 here. And so then down here, we should actually have a 4. So now what ends up happening is when we go along the quadrature, at our first point, we get 4 and 1. And then we go to our next point over. So this was the first point. This was the first odd number. First odd node. Second odd node, right? And so when we go here, we say, okay, we have to add 1 to the remaining nodes. So we get plus 1 over here, and then we added 1 to 0 over here. And so then what we get, we get the exact same thing that we got before. And this becomes a 2, right? And then if we kept going, this would become a 2. Right, because we would have some sort of node over here, and this would be 4. And so then what we get is our classic Simpson's rule, where we get S is equal to delta x over 3 times f of x naught plus 4 times f x1 plus 2 f of x2 plus dot 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 plus 4 f x n minus 1 plus f of x n. Okay, and that is the full derivation of the Simpson's rule. But if we want to write it in a more general form, we actually, I believe, we can write it like this. And I'll explain this. So if we want to really be general for some reason, we can write it like this. So this goes all the way back to the very beginning of the video. What we did was we started by creating these basis polynomials right here, right? So we have the values are 1 at the node value and 0 everywhere else. So that means that we can scale them by the function value. And then to create the polynomial between the 3 points, we take the sum of those 3 basis interpolating polynomials. And then to get the Simpson's rule for 3 points, we decided to integrate over 3 points. And then we integrate, or rather we sum over all of the odd nodes in the X mesh. And that we also know that there has to be an odd number of nodes in order for this to work, because if this doesn't exist, then, right, we have to have this formula. We have to have this form. So we have to be able to start with a 1, go 4, 2, 4, 2, 4, 2, 4, 1, right? So that's going to be the Simpson's rule. So thank you for bearing with me, and I hope that you enjoyed the video, and I will try to do more of these and maybe make them shorter in the future.